Okay, I am now officially recording, so here we go. Real quickly, what we covered last time, I'm just going to flip through the slides right quick and just hit the key points to make sure you know. Don't mess up on the signs of these. That's a key thing. Know that the term enthalpy is heat, is used interchangeably, but when you do that, it's heat at constant pressure, okay? Because if it's not at constant pressure, then it's another animal. Know and understand this really, really well. There's a universe that's made of system and surroundings. The big key thing here is really to know this. Exothermic is when a system loses heat to the surroundings. And everything else is obvious. If I just give you that one, well, if that's exothermic, guess what endothermic is? Duh, going the other way. Yes? Okay, there we go. Something I didn't explicitly mention, but you want to be able to put things in word speak that makes sense to you. When you talk about this relationship, you know that that the heat in the universe can't change, which means the heat in one of these, wow, that's really slow. The heat coming in one of these rooms has got to be equal to the heat going out of the other. Has to be. Oh, wow. That's not good. Let me take that off. Maybe just that. Okay. That if heat comes in one side, it went out of the other. Or if heat is lost from one side, it's gained from the other. So kind of use those phrases there. Again, here's just the same thing again, the way the textbook presents it, showing you to make sure you know the signs. Make sure you know the signs. Because the questions on the test will say, okay, 57 joules of heat was given off. Well, you have to know if you plug that in because it was given off, quote. You've got to know for that. That's a negative sign, right? You can't put positive 50. If 50 was given off, even though it's written positive 50 in the question, the words given off is what makes it negative. So you can't do like normally. You have to look at numbers and you have to look at the wording around it to see if it's positive or negative. Sometimes it'll say delta H is negative 50. Okay, fine. But there you have to know that the negative means it's leaving. So you absolutely, this is one of the first times where you have to be able to integrate words and numbers and know what they mean. Okay, which is a key thing of science anyway. Okay, we talked a little bit about this. You'll see with Hess's law when we do that in the lab, how that works. There were 3 conventions that you needed to know. Okay, so you need to know that it's delta H is given for a specific reaction as written. If you change that reaction, delta H or delta G or delta S is going to change also. Okay? The phase is important. And finally, we talked about writing things in line. And we've done that before. So, 2 types of problems. You're given the thermodynamic parameter and you calculate something else. Or you have other data and you calculate the thermodynamic parameter. And the thermodynamic parameters, hopefully you realize now, are delta G, delta H, and delta S. Okay, and with that, we talked about standard states. Right, and now we're getting into the punchline of where most of this stuff goes. Spontaneity. Is a reaction spontaneous? That's probably one of the biggest 2 uses of thermodynamics, is to just look at a situation and say, hey, when I mix these, is this going to happen or not? Yeah, that's it. You're able to predict what happens. Okay, and there's 2 things that we're going to do to tell if a reaction is spontaneous. What does spontaneous mean? Don't overthink it. It just means, hey, if I mix these, it'll happen on its own. I don't have to heat it. I don't have to kick it. I don't have to do anything special. I just do that and it happens. Right? Water on the side of a hill. Hey, pour it out of the bucket. That's all you got to do. It knows to flow down the hill. That's spontaneous. Okay. Non-spontaneous, up the hill. You can get water to go uphill, but guess what? You're going to have to do some work. You're going to have to figure out how to do it. So that would be non-spontaneous. Okay, so spontaneous in Jasper speak means, hey, it just happens on its own. Okay. Right, I told you not to worry so much about these only to know this basic fundamental equation, the definition of delta S. That's it. Delta S was looked at statistically, so you can combine these two equations and get these, and the three are typed out there at the bottom. Just make sure you can recognize those and plug and chug. Okay, there was just a little bit of the understanding that's behind this statistics thing. Entropy is looked at two things. It's a statistical thing, but more generally, it's just this idea that things tend to degrade. That's it. They become more random. This randomness definition is what this statistics gets at here. That randomness. Okay, that's typically, but randomness is a proxy, as it were, for disorder. And that's how it used to be normally taught. Okay. And this was just a very, very simple idea of that statistics thing. And each possible orientation of all the atoms in a particular system is called a microstate. And this is just a really stripped down, but actually a pretty darn good example of if you have two molecules in a box that's separated by pinhole, and you leave it there, guess what happens? You come back. If you've only got two atoms, you've only got four possible choices of where they can be. And those are called microstates. Well, of course, there's going to be trillions and quadrillions in some molecule, but nevertheless, the statistics holds. Okay, that's where we ended it. Right. We want to know about spontaneity. There are two things that you look at to find out if something's spontaneous. Delta G, which you'll see later, the total energy, and delta S. Okay, so here's what happens. This is a general axiom. It should be typed and bolded and put in red and everything. But when delta S is greater than 0, when delta S universe is positive, that is when disorder is increased. This is why we're all getting old and tearing up, and it's just, and your cars tear up and all of that other stuff. This is why that happens. Because of this. What this means is things naturally tend toward disorder. It's very, very unfortunate, but when something happens naturally, things become more disordered, or energy becomes less usable. That's unfortunate. Mother Nature likes that. We don't. But, so, the key with thermodynamics is you need to be able to do calculations, and you're looking for, is delta S universe positive? Okay, let's take an aside. The effect of temperature. Yep, temperature affects everything. Yes, you know with K, equilibrium constants are constant for a given temperature, right? And you've seen three equations where you have the 1 over T minus 1 over T prime, right? Looking at the effect of temperature changing. So temperature and temperature changes are always a big deal in chemistry. So we will just consider that again because we always do. You've seen these before, both of these before, in different contexts, so let me go over this really quickly. There's the distribution for temperature at T1. Distribution of what? Distribution of your molecules. Remember, if you're at 25 degrees C, say you are at 25 degrees C, and 25 degrees C represents that line. And remember, temperature is measuring what? The vibrations, the rotations, and the translations of your molecules. Yes? That's what it's doing. Okay, so why is that? Oh, man, that's a bad shortcut. I shouldn't have put that as a shortcut. Wow, all right, I gotta fix that. Okay. Right. So, remember that temperature measures the vibrations, the rotations, and the translations of your molecules. This is a chemistry class. That's the motions that we care about. Vibrations, rotation, translation of individual molecules. And the sum of all of those molecules are what cause the temperature. Okay, so here we go. So let's say this is, and I'm having to write with a mouse. This is really ugly. Okay, so let's say this is 25 degrees C. The punchline here is, at 25 degrees C, if I have a beaker of water, not all of my waters are vibrating at, quote, 25 degrees C. Some of them are moving a lot faster than others, and some of them are moving slower. So you have to remember when you do a temperature profile, it's an average, and I think you know that. So now, when I move to increase the temperature, oh, fat chance drawing a straight line with that. So when I move to an increase in temperature, the average moves up, and let's say this is 60 degrees. All right, so this is supposed to be review. So as that moves up, then the average moves up. But you still have, even at a higher temperature, a few molecules moving as slow as the slow ones at 25 degrees C. But what you have is some that are moving much, much faster. So the average moves up. That's the first thing you need to realize. Now delta S, let's look at this with respect to phase changes. Right? Remember this curve? Okay, so you start out at 0. This is absolute 0 degrees C, which means you have no vibrations, you have no rotations, you have no translations. You're as cold as you can get. Why? Because if there's none of these, the temperature is 0. It's absolute. Okay. So here's what you need to know. Now notice this looks a lot like the heat diagram, but what is this? This is what you need to know about. This is the punchline here. This is entropy. So entropy behaves the same way, and let's see if we can rationalize it. Why is this important? Because when you want to know if something's spontaneous, this is going to make it be important. You might have questions about delta S for melting or temperature gains. Okay, so we're looking at temperature gains here. You know how molecules behave. Okay, so what happens? As temperature goes up, things get more and more and more and more erratic, right? So you can see that probably as you go up in temperature, entropy is going to go up, and indeed it does. So here's what happens. Start at absolute 0, you're heating something out, a block of ice at 0 degrees. So as you heat it up, now remember, this is not the heating. As you heat it up, the entropy starts increasing. So what happens? Why? Because as you heat it up, they're vibrating and rotating and translating a little bit faster. They're moving a little farther apart, and that's more chaotic. That's more random. Well, then what happens when you get to 0 degrees C? All of a sudden, entropy goes nuts. It goes it does. It goes straight up. Why is that? Well, because now you have things going from one phase, a solid, to a liquid phase. Well, let's think about that. If you have a solid block of ice, the molecules are limited. They're confined to that space. But if you now melt that, it gets spread out. It can move anywhere. It can get as thin or as thick as it wants. So it has a lot more what? Degrees of freedom. Okay, so the way you would look at that is, when I go back, this is written on the screen. Okay, so now I might have to go back. Okay, so just look through that. Now I'll go back to this is a screenwriter, so you know. Sometimes I etch with what's in the program. Sometimes I use a screenwriter. A screenwriter, it stays on the screen no matter what's behind it. Okay, so this entropy thing right here, this increase. So what do we have here? Well, when you go in, you have a lot more of these. That's the way I rationalize it. But you got a lot more microstates. You got a lot more possibility. Or another way to look at it is you got a lot more freedom, right? The molecules are free to move about the cabin, as it were. I mean, you're not confined. You're not confined to that cube of ice. Now you've got freedom to flow and move and do what you want to do. Okay, a lot more freedom. And that's why entropy goes up tremendously between phase changes. Okay, continuing the story, now it continues up. So as the water gets warmer and warmer, the molecules vibrate more and more. So entropy goes up. And then you get to a gas phase. And look how huge this is. There's much more of a change than here. Well, that makes sense. You should be able to rationalize that. Why? Look at how much freedom you have when you go from a liquid to a gas. I mean, you got water at a cup of, you got a cup of water in a room. Now, when you boil it and turn it into steam, what happens? Now the molecules can go anywhere in the room. That is a lot more freedom, a lot more randomness, a lot more disorder. And so there's a huge jump in entropy. And then it goes up incrementally after that. Because as you continue heating it up, then the vibrations, rotations, and translations are bigger. And so that's walking you through in excruciating detail what happens to entropy. Hopefully it'll help you understand. Now, that's the concept. You got two things. You got concept questions, right? This could be turned into a concept question. Or you've got just the math type of questions. Okay, so now that you understand the concept. Right, and it's going to be spontaneous, right? So depending on your conditions, this may or may not be spontaneous. And what we're going to look at next is an example I pulled out that is really a really good example. Oh, I just lost all of that, didn't I? Okay, is a really good example. Because let's say right here, see this freezing line? Guess what? So water naturally freezes at minus 10 degrees C, yeah? Okay. But it doesn't freeze at 10 degrees C. So how could we look at that? So we're going to look at the math of that. And you're going to actually understand for the first time why it is. How does water know? What is so special about minus 10? Because it's the same system, same molecules, right? Minus 10. Why are they going to freeze? And why is it not going to freeze at positive 10? Yep. Okay, so here we go. That's where we're headed next. It's a good illustration. The reason I like it is it's a really good concept, but it also teaches the math behind it. Well, I'm not going to do that. I'm going to do that right there. I'm going to do that in a couple of minutes. Okay, we're going to get a little more background first. Okay, yeah, let's look at delta S more generally. So these are the easy questions. So can you guess the sign of delta S by answering a question? These are good, easy concept questions. So I'm going to ask you a few questions, and then you're not going to do it quantitatively. You're not going to get a number. You're going to do it qualitatively. Just say yes or no. It's like, does it get bigger or does it get smaller? I don't want the number. I just want to know bigger or smaller. So oftentimes, standard fare type of questions are, can you tell me the sign of delta S? Is delta S positive? Well, you can't do that if you don't understand the concept. Okay, so what I normally do is it's a question that's getting at this. Did the system or the particles or energy that make up the system, did they become more disordered or spread out or random, or did they get more freedom, or did they become less restricted or confined? All of those are my paraphrases for this is how you see if entropy is getting what? More positive. Okay. And remember, that's towards spontaneous. So delta S positive. So let me write some things down here. Okay. So let me see if I can do that. So all of these indicate, oh, they got that lag. This program is not going to work. I got it right with a mouse. Sorry. That thing is just way too slow. Okay. Right. So what all of these mean is delta S is positive. And what these also mean is it's spontaneous. Okay. Wow. That's supposed to be the word spontaneous. Okay, so let's try one more thing. Can I move it around a little bit? Yeah. There, I'll make that look hard. Okay, so this is the whole key to these. Okay, so unfortunately I have the answer down there, so don't look at the blue. Okay, so you have 1 mole of liquid at 25 degrees C, and you're comparing that to 1 mole at 50 degrees C. So in going from one to the other, what happens? Delta S is positive. Why? Because at 50 degrees C, you're going to have a lot more random motions. Yes? You're going to have a lot more random motions, a lot more movement. And because of that, it's going to be a lot more disordered. Okay? Since they're going to be moving around more, you can look at it, they're going to have more freedom. They're going to be translating more. Okay, so in going from 25 to 50 degrees C, delta S is positive. So if you decrease temperature, you also decrease delta S. And, and you know this. Why? Because I just told you right there. You can see the relationship with temperature there. It's going down. Okay, but you can rationalize it. Okay, so this is a pretty good one here. So benzene reacts with oxygen to give carbon dioxide and hydrogen. So how can you look at a stinking reaction and just look at it and tell? Well, it's not really that terribly, terribly difficult. So let's look at this reaction here. Okay, so remember, we're looking for, in this case, freedom or disorder. So look at what we have over here. Let's count the particles. I've got one of these, and what do we have? 7.5 of those. Oh, but I don't care about the liquid. Oh, I just care about the gas. That's right. Because remember, liquid standard state thing. So look at what I have in the gas thing here. I have 7.5 gas particles. And the gas is going to be the ones with all the entropy anyway, with most of the entropy anyway, right? Because they're free to move about. But what do I have on this side? 6 gas particles. So guess what happens? I now have fewer particles that can move about the cabin. So what I actually did was I lost entropy. Mother Nature may love this in terms of heat gain. This is going to be exothermic. Mother Nature says, good, that's spontaneous. That's exothermic. I like that. But entropy-wise, she says, I don't like it. And you're going to see in a minute how we balance it out. When heat says, I want this to occur naturally, but entropy says, no, I want to go uphill. And delta H says, I want to go downhill. So what's your punchline? Is the reaction going to happen or not? Is the reaction going to move downhill naturally, or is it really an uphill thing? We'll pull the contradiction between delta H, heat, and delta S, work energy, pull in opposite directions in a minute. But for now, let's look at this. So you can see delta S is negative, and I tried to draw a hokey little picture out here. So the red dot there means a half a particle. So I have 7.5 particles on this side. And then I essentially combine some so that I only have 6. So this is going to be less freedom. Well, you can logically say, well, sure, there's not going to be as much movement with 6 particles as there's going to be with 7.5. Okay, that's kind of a clumsy definition, but that's still the way I would teach it. The way you really teach this, though, the way you really do it, is you would say, see, 7.5 are going to 6. I just want you to know, rationalization, you can kind of dummy it down in your head, but it looks like this. And this is what Boltzmann did. Can I find it? Oh, pooh. Hang on. Right there. Okay. So what happens is your number of particles is less. And so what's going to happen is you're going to wind up with a lower number when you do the statistics with the microstates. See, what you did was, see, if I had another particle here, this is just 2 particles. What if I had 3 particles here? Then what? Then I would have a whole lot more states, right? I would have a total of 9. If I did 3 particles, I would have a total of 9 microstates instead of 4. I've got 2 particles, I can square it, 4 microstates. If I had 3 particles, I could do them 9 ways, right? All 3 of them could be in this box, all 3 could be in that box. 1 and 2 could be in this, and 3 in this. 3 could be in this box, and 1 and 2 in this, right? Y'all got it? You could have 9 microstates, and those microstates define S. So that's where this microstate thing comes in. Okay, so as you get fewer particles, it's like going from 3 to 2. If you had 3 particles here, you would have what? 9. But if you then take 1 particle away, you now only have 4 microstates. And you did what? You lost your entropy. Okay, there we go. So that's how it's really taught. But sometimes it's easy to just rationalize it in terms of freedom and motion. Okay, now this is quantitative, so you can see. So the punchline there is, whether you understand why or not, you go to fewer particles, then that's moving entropy in the negative direction. Now you know why I told you had to pay attention, like thermodynamics, to the phase, because here liquid is standard state. We're going to forget that. If you didn't, this would be 9 and this would be 8.5, and you would actually think it gained in entropy, but it didn't. Why? Because the solid and the liquid compared to a gas, they don't have much movement. Okay, let's look at one more. How about if I take sodium chloride, a solid? So what does this mean? I got a spoon of salt, and it goes to Na plus and Cl minus aqueous. So what is? Oh, I lost my negative sign there. So what does that mean? I just took the salt and I stirred it, dissolved it in water. That's what I did, right? That's so. How did entropy do that? Entropy loved it, really. Oh, it loved it. Why? Because you're bound to a solid, and now you can move anywhere in the liquid, because you're now aqueous. So this is a humongous increase in entropy. So again, think about it in terms of freedom or movement. So let's look at this is a good example right here to show you the phrases, right? So what could I say about the salt now? Are the particles making it up? There's certainly a lot more disorder. There's certainly a lot more spread out. They're certainly moving around a lot more random. They have a lot more freedom. They're less restricted, and they're less confined. So that's a pretty classic example there. Okay. Boom, boom, boom. Here we go. The sign of Q. So now we've talked about the sign of Q, heat. Okay, so this is kind of weird. Delta H is related to Q, and so is delta S. Okay, so they can both be talked about in terms of Q, in terms of heat. Okay, remember, we have systems, surroundings, universe. So we're interested in what's happening with our system. We have some chemicals or whatever, and we want to see what happens to them. So we're going to look at our system. So if Q is negative, well, you know that. If Q is negative, then heat flows from the system to the surroundings. And delta S is going to follow that. Okay, so let's just look. If delta S is positive, and you know this, you have heat coming into the system. This is just kind of a review of where Q is. Okay, because it's going to relate to this. Right. Let's see. Okay. If we have a revert. Okay, I've got to do an aside of this from where I'm going here. And I think we might have talked about this a little bit last time. But this Q reversible. Remember, if Q is reversible, it's a smooth change. It could be thought of as kind of sort of being at equilibrium. Yep. So anytime you have Q reversible, we just write a Q, we drop it. We drop the reversible. Okay, so in most of these, you assume that Q is reversible. When we normally write reversible here is when we're comparing it to a Q that's not under reversible conditions. Okay, so that'll make more sense here in a couple of minutes. Okay, but right now we're concerned about what? The sign of Q, because that's going to affect the sign of S. Okay. Okay, so hold that thought.